This is the second lecture on binary choice models. So in a previous lecture, we discussed the setup of the binary choice models and the fact that we can estimate parameters using maximum likelihood. This is the continuation where we look at inference from the binary choice models. So just a quick reminder, a binary choice model is a model that we use when our dependent variable is a dummy variable, and it's an alternative to the linear probability model. The basic idea in the binary choice model is that we model this probability, the conditional probability that y is equal to 1 given some x variables. And I just write x here to represent all the possible x values that we have. And we model this as being equal to some function of zeta, where zeta depends on the x variables like this. It's the traditional linear representation of the x variables. So zeta is linear in parameters, but it doesn't have to be linear in data. One of the x variables could, for example, be the square of another x variable. And we also allow dummy variables among the x variables. So this is a very different setup from the linear probability model, which is just a regression model. This is not the regression model. We do not model y as a function of the data and the parameters plus an additive error term in this case. So this is the setup for a generic observation. Then we can add subscript I to all our variables y, x, and zeta to say that this model holds for each observation. So if I then have a random sample of yi, a bunch of observations, xi2 all the way to xik, if this is observed for y is equal to 1 to n observations, then I can use the maximum likelihood method to estimate the parameters beta. So they will give me estimates, which I'm still going to call b1 through bk. These are not OLS estimates. We instead call them maximum likelihood estimates. Depending on the choice of f, we also call them logit estimates if f has a particular form, and probit estimates if f has another particular form. The only thing we require on f is that it should have as a domain all of the real numbers, and as its range should be 0 to 1. So the first thing I want to discuss are the fitted values from the binary choice models. So I have now estimates b1 through bk of these parameters beta 1 through beta k in the binary choice model. It doesn't matter if it's probit or logit or even another form of this capital F function. From this I can calculate what is called z values. So what I do then is just start with the zeta expression, and I replace the unknown betas with the estimated b's. Of course, I don't know the betas, so I don't know the zeta values either, but the z values I can actually calculate. Since the b's are estimates of betas, we can say that the z's are estimates of the zetas, honoring our tradition of using Roman characters for things that we observe and Greek characters for unknown stuff. The z values are my first step towards the fitted values in the binary choice models. Remember that the actual probabilities are equal to this function f of my zeta value. Now I have an estimate of my zeta value, which is my z value. So if I plug my z value into the function f, I will get estimates of my probabilities. And those estimates are called fitted values in binary choice models. So we find the fitted values simply by plugging the z values into the capital F function. So now I have one fitted value for each observation. And again, since the zi's are estimates of the zetas, the yi hats will be estimates of the probabilities. We can use exactly the same method to do out of sample predictions. So if I have estimated this model using a setup of observations containing n observations, I can do the predicted values for an observation that is not in the sample. All I do is I just calculate the z value for this out of sample observation. I need to have the x values, obviously. I calculate the z value, and then I can find the predicted value. Then I can find the estimate of the probability that y is equal to 1 for this particular observation. So let's have a look at fitted values in Econometrics software. Here I have this data on the number of hours that students have studied for an exam and a dummy variable pass, which is 1 if they pass the exam and 0 if they fail it. We considered this data previously in the linear probability model. And the linear probability model has the advantage of being very simple. We can easily estimate the parameters beta 1 and beta 2 using OLS. And the fitted values are just like the ordinary fitted values. And they are interpreted as the estimated probabilities as well. But remember, they have this issue of predicting sometimes outside the 0-1 interval. So to remedy this problem, we use the binary choice model, and we are free to choose between probit and logit. So let's do both. So let's first do logit binary. So we do pass as a function of hours. Okay. So these are my logit estimates of the beta parameters. So I have copied the logit estimates into Excel here. So from these estimates I can calculate my z values. So let's do that. So my logit z values, I just use the logit estimates and my x variable like this, just a linear function, b1 plus b2 times the x value. Like this, and then we just copy the z value. So here are all the z values. From this we can do the logit y hats, the fitted values. Remember, all we have to do is just to plug the z values. The z values is b1 plus b2 xi2 plus bk xik. And to get the fitted values, all we do is we plug the z value into the function f. And for logit, this f of x is 1 over 1 plus e to the minus x. So let's do that. So we do 1 divided by 1 plus x minus, and then the z value, which is indeed 2, and parenthesis like this. Copy this down, and these are my estimated probabilities or predicted probabilities. So now that we have done the binary choice model, we are guaranteed that these estimates will be between 0 and 1. For example, for this observation that studied 501 hours, in which the linear probability model predicted 127% probability of passing the final, we predict, well, at least to 2 decimals, 1.0, 100%. But if you look at the decimals here, it's actually 99 point something. So let's do probit as well. We go model, limit dependent variable, probit, binary, pass, hours, okay. These are my probit estimates. Just copy these. And note that when you copy, if you copy the minus sign from Gretel, you'll actually get a wrong minus sign. So Excel will not recognize this as a number. So put the correct minus sign. So the probit z values are pretty much the same. We just replace the b1 and b2 and take them from the probit estimates instead. Copy down, and then we can get the y hat probit. The f function for the probit model is the CDF of the standard normal, and it's called norm, S for standard, and distribution. So you just take the z value that's in f2, and you want the cumulative, the CDF. So you put a 1 here. So this is the y hat from probit. Copy this down. So from this little experiment, I want you to notice a couple of things. First of all, the actual estimates in the logit and the probit model are actually quite different. The logit estimate is almost twice as big as the probit estimate. But keep in mind that these numbers actually have no direct interpretation. They are just part of the computation of the z values. So in an actual interpretation, in terms of the estimated probabilities, then they are actually very close, as you can see. And this is generally something that tends to be true. In most cases, it doesn't matter that much if you pick logit or probit. They will come up with approximately the same estimated probabilities for y equal to 1, even though the parameter estimates are slightly different. You can, of course, get these fitted values right in Gretel and Evius as well. I just wanted to demonstrate a little bit more carefully how they're calculated. So if you go to graphs, fitted values, and pick, for example, by observation number, then you will have all the fitted values going from 0 to 100. The red dots are the actual value of y. Y can only be 0 and 1, and the blue x's are the fitted values. So for example, for the first observation which failed, we can see that the fitted value is, I don't know, 0.75 something. Double check that with Excel. 0.73 is the value that we calculated. Well, actually those were logit ones, so 0.75 is the one we calculated in Excel. Alright, so this is one of the important inference part that we can do from binary choice models, finding fitted values. Next, let's move on to the beta parameters. So keep in mind, the beta parameters really have no direct interpretation. If you want to, you can see from here that, for example, beta 2 is the partial derivative of the zeta variable with respect to x2. But that doesn't really mean anything because the zeta value is just sort of a helper variable to understand the theory. The zeta value in binary choice models are not probabilities. So the beta values, or its estimates, the b values, they actually have no direct interpretation. We can't look at this number and say something like, aha, if hours increases by 1, then something something increases by 0.06. There is no such interpretation like there is in the linear probability model. Instead, what we are interested in is the change in the probability that y is equal to 1 when I change one of the x variables. So to illustrate this point, let's consider a simpler model where we only have one x variable. So my probability that y is equal to 1 conditionally on a single x variable is now a function of my zeta. Well, there's no change here, but my zeta is just equal to beta 1 plus beta 2x. What I want to figure out is when x increases a little bit, how does that affect the probability that y is equal to 1? That's the marginal effect. Think of this in the example terms where y equal 1 if you pass the exam. The question is, if you study 1 more hour, how much will that increase the probability of passing the exam? So all we have to do is to figure out the change in this probability, which is also the change in the expected value, of course, with respect to x. And that is then d f of zeta dx, because the probability is f of zeta. So to do this derivative, we just use the chain rule. This is a composite function. F depends on zeta and zeta depends on x. So we do the outer derivative, that would be f prime zeta times the inner derivative. And the inner derivative is the derivative of zeta with respect to x. And that's simple, that's just this constant here. So that's beta 2. So this is the important number in binary choice models. This is the marginal effect. You can probably quite easily see how this generalizes. If I have more explanatory variables, x2, x3, and x4 and so on, and I want to look at the marginal effect of one of the explanatory variables, then the whole thing will look the same. The only exception is that if I want to do it with respect to x3, then I'm going to get beta 3 instead. So we have the following results. In the binary choice models, the change in the probability that y is equal to 1 when one of the x variables changes a little bit is the derivative of this f function times the beta parameter. Now this is obviously unknown, both because we don't know zeta and also we don't know beta. But we have estimates of both of them, so we can estimate this marginal effect. And to estimate this marginal effect, we just replace zeta with z and beta with b, and we get the estimated marginal effect like this. So the next question is then, what is this derivative of capital F? Well, again, that depends on which f function you have selected. If you have selected the logistic function doing logit, or you have selected the CDF of the standard normal doing probit. So for the logit model, the derivative of f is given by this expression. So once we have this expression, figuring out the marginal effects is pretty straightforward. For example, let's consider this individual, this student here. Let's focus on the logit estimates. This student has studied 129 hours and from the logit estimate has a probability of passing the exam which is 75%. The question we want to answer is, how is that probability affected if this student put in one more hour, going from 129 to 130? Well, the answer is pretty straightforward. We have the z value there, that's an estimate of the zeta. So you take this z value and you plug it into this formula. That will give you the derivative. Finally, remember the marginal effect is the derivative times the beta parameter. So you simply multiply that with this b2 parameter, and that will give you the marginal effect for this student. All students will have a different marginal effect depending on how many hours they study. And if you carry out this, you will see that students that have studied a lot, like the one on row 16, will have a much smaller marginal effect than students that have not studied as much. If you want to figure out the marginal effect for probit models, then the derivative f prime is simply the PDF of the standard normal. Maybe you remember from probability theory that the derivative of a CDF is the PDF. And the PDF, probability density function of the standard normal, is given by this expression here, where I have fixed the typo. It should be an X, not a zeta in that one. Alright, so for the last part of this lecture, remember, we cannot interpret the actual value of the beta parameters or its estimates in the binary choice model. However, we can interpret the sign. And the interpretation of the sign is as follows. If beta j is equal to 0, if one of the beta parameters is equal to 0, well, then the zeta value doesn't depend on that particular x variable. And if that's the case, this probability will not depend on that x variable either, because this probability depends directly on the zeta value. So that's important. So if we find, for example, that this coefficient is very close to 0, then we could conclude that ours have no effect on the probability of passing the exam. So 0 does have a meaning. Now in this case, because the standard error is so small, we actually have a z-value which is very large, 3.95, certainly much larger than the 95%, 1.96. So this coefficient is definitely significantly different from 0. So ours does have an effect on the probability of passing the exam. If, on the other hand, beta j is strictly greater than 0, well, if you look at the expression, you see that that means that zeta increases with xj. The bigger the xj, the bigger the zeta. And we also know that this f function is a strictly increasing function in zeta. So that in turn means that when xj increases, the probability that y is equal to 1 increases. So moving to my example here, this is significantly greater than 0. So even though I can't interpret this particular value, 0.016, that means nothing. I can say that when you increase the number of hours studied, there is a significant increase in the probability of passing the exam. And we can draw a similar conclusion for estimates that are negative. So had this been negative, we could then draw the conclusion that increasing this explanatory variable will decrease the probability that y is equal to 1. We can't say by how much. To say that, we have to calculate the marginal effects.